Good evening, one and all present here. And I welcome you all for the fifth day of online one-week faculty development program, Electric Vehicle Drive System. Today's topic, Internal Permanent Magnet Design for Electric Vehicle. Today's session is going to be handled by Dr. S. Prabhu, Associate Professor, School of Engineering, Department of EEE, Mohan Babu University, Tirupati. I'm glad to introduce Sir to the participants. Dr. S. Prabhu has received his bachelor degree in Department of EEE from BLB Janaki Ammal College, Tiruvannamalai. He has completed his master's in power electronics and drives from Aranai Engineering College, Tiruvannamalai. He has completed his PhD program in Anna University. His research area is performance investigation of doubly salient permanent magnet switch reluctance motor. And he has published more than 2 IEEE papers and 10 IEEE conferences. Also, he has published 30 plus international journals and 30 plus international conferences, and he has active speaker in several FDPs and active trainer in several workshops, and so on. I'm happy to welcome you, sir.
Thank you, sir.
I hand over the session to sir. Thank you, sir.
Thank you, sir. Good evening to everyone. So I first of all want to thank the management and head of the department and Arul sir for giving me this opportunity. So now we will enter into the session. So in our today's session, I'm going to tell you how to design an internal permanent magnet motor for electric vehicle application. And myself, Dr. S. Prabhu, Associate Professor of Mohan Babu University. And in today's content, we are going to discuss on estimation of motor power for EV. Because before going to a design of any machine, we need to know what is the requirement. So without knowing the requirement, we can't be able to design a machine, especially for application-oriented purposes. So that is the first topic. So what is the required power for the motor? And followed by that, we are going to discuss on finite element method for the design of IPM motor. And after designing, we should validate the result, whether the result obtained is correct or not. So for that, we are going to perform the electromagnetic analysis. And in addition to this, we are going to see what are the losses and what is the major drawback in the internal permanent magnet motor. Not only in internal permanent magnet motor, but this drawback is quite suitable for all permanent magnet based machines. And coming to our topic, first one is estimation of motor power for EV application. Since we have considered EV as an application, so for designing an EV motor, we should first of all assume what is the value kilogram of our vehicle. So first we should know what is the kilogram of our vehicle. That is our mass of the vehicle, right? And then what is your range? So in what speed it is going to get run. So I'm going to consider it as 70 km per hour, right? So now consider we are having a road surface here, and in this road surface we are going to have a vehicle here. Consider we are going to have a car here. If the car wants to move in the forward direction, right? So if a car is moving in a forward direction, there is some forces will be opposing the direction of the car motion. So in that, if you see the wheel, right? So in the wheel there will be some tire will be there. So consider the portion of the tire here. So if this is the position of the tire, such that the the area of contact with the road surface is very less. So in this case, the rolling resistance of the wheel will be very less. So we can be able to move the vehicle as easy as possible. But if the air is very low, what happens? The contact area which is associated with the tire and road will be increased. So the rolling resistance value will be increased. Right? And next one is gradient. Suppose this is our road surface and the vehicle want to move in a surface which is fixed in this attitude. So if this is a vehicle and vehicle want to move in this direction. So here this angle, there is a difference in the angle here. Right? And this angle is said to be as gradient angle. Right? And with respect to this condition also, we need to consider while designing a motor of an EV application. And next one is aerodynamic losses. So whenever a vehicle move in a forward direction, suppose 70 km/h, what I assume for this case study is 70 km/h. So if a vehicle is moving in a forward direction in much speed, the same 70 km/h will be in the opposite direction. Right? So that force also I need to overcome, then only the vehicle can be able to move. And then last one is the acceleration force. Right? So these are the four forces that I need to overcome if I want to run a machine from one place to another place. So now we will discuss one by one. So in this condition, so here the first one is rolling resistance, and rolling resistance is nothing but rolling coefficient into mass into acceleration. So here I will consider the rolling coefficient value as 0.01. The reason here is the vehicle will move not only in the road surface, not only in a sandy area, but also sometimes when rain is coming, the sand area will get somewhat moisture content and the resistance will be somewhat high. So here I consider a normal condition. So I have taken as 0.01 and I assume I want to design a mass of the vehicle as 250 kilograms and we know the acceleration is 9.81. And if you substitute this one, we will get a force as 24.5 Newton meter. Right? So then, what will be the opposing force? Opposing power is required to overcome this rolling force. So for that, so rolling force into velocity. So if you substitute this rolling force into velocity, so here this 1000 divided by 3600 nothing more is a unit conversion of kilogram per hour into meters per second square, right? So at last we will get a value of 476.875 watts, right? So this is up to our rolling resistance. So when we come back with our gradient, so here we are having theta, and theta I already mentioned. So this is the angle of theta in which the vehicle is trying to move in a slope manner. So if your vehicle is moving in this case, it is said to be as forward gradient. So if your vehicle is moving in a downward direction, and it is said to be as a negative gradient. So generally, while designing an EV based application, we will take it as zero because suppose if it is a three-wheeler, the three-wheeler is not going to move a far distance. So from one instant, no longer it is a 1 kilometer, we will move in auto or 2 kilometer or 3 kilometer. So in that case, there is no more gradient will appear. Suppose if you are designing a vehicle for an long drive, suppose consider it is a car, then definitely we need to consider a gradient there, right? So I consider a minimum gradient of 30 degrees. Okay, so the maximum we can go up to just 40, 45. And if you substitute the value, we will get around 126.25 Newton. And the next one is aerodynamic force. And here the important aspect is nothing but this AF, right? So AF is nothing but the front end area calculation, right? So how to calculate this front end area? So if you want to calculate this front end area, we need to consider a three-dimensional view of a bike or a car. We need to consider a three-dimensional view of a bike or a car. And then we need to convert this three-dimensional view into a two-dimensional aspect so that we can be able to get height of a vehicle as well as the width of the vehicle, right? So exactly we can't able to determine what is the height and what is the width of a vehicle. So height means we need to include the person who is sitting on the vehicle with helmet. And width of the vehicle means nothing but the handbar of an bike, right? And adjusting value means, see here, for adjusting value for car is 85% as per the standards, and for the bike is 70%, and for the truck or lorry it is around 100%. So we no need to consider the adjusting value for the buses or cars or the trucks. And then, so these are the constant values what we are assuming, and here is the coefficient value. So this is depend upon the condition of the, right. So it is 0.88, and adjusting value we have taken it as 0.89. Right? So if we substitute, we will get a aerodynamic force value as 182.202 Newton meter. So to oppose this force, I need to have an acceleration value, right? So I will get an power which is going to oppose the aerodynamic force as 3538 watts. And here I would like to say about how to calculate this height and width. Suppose this is the area in which your bike is placed with the person is sitting here, right? So as a person means we cannot be able to say the entire area. So here only the person will be allocating his space, right? So this area has to be neglected. So for that purpose only we are giving the adjusting values. And then the last force is acceleration force. And the acceleration force is having mass into acceleration, and here the acceleration should be considered as the initial value, right? So here, right. So here why I consider this 0.486, because so we know the acceleration nothing but it is the dv by dt, right? dv by dt is the acceleration. So it is final value minus initial value divided by the time. So time is, if you want to have a quick acceleration, we should have a less value of time, right? So suppose your acceleration value is 70 kilometer maximum value, and initially it is 0. So everything divided by the 3 or 4 seconds of time, you will get some value, right? So that value we need to substitute here as an initial acceleration, and you will get an force acceleration as 121.5, right? So if you add all the force what we have developed, and it is around 5.5 kilowatts. Okay, so this is the power required which has to be designed for an electric vehicle. If I want to design an electric vehicle for a weight of 250 kilograms, right? So here at the beginning I have considered the mass I need, the mass of a vehicle should be of 250 kilogram, and the kilometer per hour I consider is 70 kilometer per hour. And if it is the case, and the power rating of the motor is 5.5 kilowatts, right? Suppose if you are designing the motor with another mass as 200 or 150, or if you are designing for a car, then the entire value gets changed. So you need to concentrate on the value of this acceleration coefficient, because this will change with respect to the conditions of environment. and the rolling coefficient also will change with respect to the environmental conditions, right? And this theta also has to change if you are designing for a three-wheeler application or a bicycle application. For bicycle and three-wheeler, we generally consider this gradient value as 0. And now we came to know the power rating of an internal permanent magnet motor. So by understanding this basic concept, and this is a background for designing of any motors for EV applications, right? So after knowing this, we are going to enter into the design of finite element analysis, and I'm going to explain this one with respect to a case study. First, we will discuss what is the characteristics of an internal permanent magnet motor, and followed by what are the types available here, and how we can be able to design a motor by using finite element analysis. So now, what is this internal permanent magnet motor and why we want to move towards this internal permanent magnet motor? So nowadays, we need to have a high power density based motor for an EV application. Suppose if you consider at the starting, Tesla preferred induction motor, and then in future they are moving towards BLDC motor, permanent magnet BLDC motor, and again they skipped to permanent magnet synchronous motor, and now they are focusing on internal permanent magnet motor. The reason why we are going for this permanent magnet based machine is I already mentioned now, to have a high power density. And the drawback here in this internal permanent magnet motor is, since we are having a magnet in the rotor, it will lead to a development of an cogging time. Right? So whatever we do, we can't able to make this cogging torque as 0. We can able to reduce the cogging torque as much as possible. So the important constraint in the design of the IPM based motor is the design of magnet sizing, right? So for that we should know what is the basic requirement why we are placing a magnet. Right? So if you understand this, we can be able to overcome how to design a magnet for any machines. So here, the main agenda for placing a magnet in the rotor is to develop a flux in the air gap, right? So then only the rotor tends to rotate by cutting the flux lines, which is developed by the stator, right? So for this, the basic equation, right? The basic equation for designing a motor here is, not only for this motor, this is available in the textbook A.K. Shahani, the generalized design procedure for any motors, right? So here we know the power equal to C naught D square L ns, right? So where the C naught equal to 1.11 AC into kW into B average into 10 to the power minus 3. So after solving this, we will get a value of D and L, right? So further we need to consider the value of L by tau, 0.7, right? So why I consider 0.7 is, here we are going to consider a rectangular pole structure in the state, right? So for that purpose only we are considering a 0.7. So if the shape of the stator is changing, means this ratio also will be changing. Right? And this is available in A.K. Shahani for electrical machine designs. For the magnet design, we can be able to refer Miller, right? So TJE Miller is an excellent textbook. So we can be able to refer the how to design the permanent magnet for an any machine, right? Now, so the agenda, what we want to understand is what is the purpose of magnet and when we are keeping this magnet inside the rotor core, right? So the difference between a BLDC motor and an IPM motor is the BLDC motor, the permanent magnet is placed in the outer periphery of the rotor core. Whereas in case of this IPM motor, the permanent magnet is embedded inside the rotor core. So that is the only difference for this IPM based machine. Moreover, the working principle under is same as PMSM, right? And then uh, so now we will see what are the different types of motors available here. So here the first one is said to be as a lateral magnet. So lateral magnet is nothing but the magnet is in the rectangular form. And here we need to arrange the direction of magnetization such that two adjacent, right? So we will have so two adjacent permanent magnet should not be in the same direction of magnetization. So the direction of magnetization has to be reversed between the adjacent magnets. Right? Otherwise, what happens? The flux will rotate in the same core itself. So more value of Coggin torque has to be appeared for this motor. Right? So to avoid this, we need to have a different direction of magnetization. And seeing this flux pattern, we can be able to see where the flux density is being higher. So the flux density seems to be higher in the back ion, right? Back ion of the stator core, and the flux is transferring from the stator to rotor, right? So if you see, in this case, the flux is not transferring at a time when compared to here. So here the flux concentration is more, here it is somewhat less, and here it is very, very minimum. And in the this side, so this is the flux direction. And if you see the rotor alone, so you can be able to see the flux path here. So this one is said to be as a shortest flux path. So why we are preferring a shortest flux path for this IPM based motor means then only we can be able to have less iron loss in this machine, right? So the winding pattern also plays a vital role in the design of a motor. So there are two patterns, one is long flux, other one is short flux. So here we are preferring a short flux based machine. So here short flux means the flux will transfer in this way only, right? So this is said to be as a short flux based motor. So long flux means the flux has to transfer the entire machine. So that is said to be as a long flux. So we won't prefer long flux for this IPM based motor. So this is the torque characteristics what we have taken for a case study. And here we have a torque, a maximum of 15 and an average of 9.77 and sorry, a minimum torque and an average of 12.5 and followed by the torque ripple as 0.4. Right? So now the next problem starts in the design of your machine. Right? So up to now we have discussed the Coggin torque and the flux pattern, and from this table we are seeing torque ripple. So these are the three important drawbacks what we need to address while designing any machine. Right? Now, so how to estimate this torque ripple? So torque ripple is nothing but maximum torque minus minimum torque divided by its average value. So that results in the torque ripple graph. Right? And now, if you use a curved shaped magnets, so in previous case we are using a lateral magnets and now we are using a curved magnets. So we can be able to see the ripple content is reduced, right? Not only the ripple content is reduced, but also the average torque also is reduced. So by designing a motor, the important parameter what we need to consider is torque value. So torque is an important parameter by designing any machine, not only the IPM. If you go for induction motor, if you go for SRM motor, if you go for synchronous reluctance motor, torque is the key parameter for designing any type of machines, right? And this is another type of curved magnets, and this one is nothing but insert lateral, right? So insert lateral means, so here we are having some air gap. So air gap is nothing but, we will say it as flux barrier here, and this is nothing but magnet. So flux barrier also is available, magnet also is available. That means if you are using a reluctance, we will get a high torque, and if you are using permanent magnet also, the torque value will be increased, right? So a proper design has to be considered to have a high torque here. So if you see, the torque ripple is further reduced to 0.14, right? And it won't compensate on the average torque. Now, these are the other different types of internal permanent magnet based motors, right? So the first one is one layer motor, and second one is two layer motor, and third one is three layer motor. So what is this layer states to? So if your requirement is, uh, now we are going to see how to design a 5.5 kilowatt based motor. So in this case, it is not recommended to use one layer, right? So better go with three layers, right? So how can I say it is three layer is suitable or one layer is suitable? So if you are going with one layer, more power torque is required. More torque is required. So the thickness of magnet has to be increased here. So if thickness of magnet is increased, automatically the length of the magnet also has to be increased, right? So the carbon torque will be increased more. So that leads to a major drawback in the machine, right? So to overcome that, we are going for segment based magnets, right? So if you see a prototype model also, if you are using a magnet for a greater stack length, if you are using a magnet for a greater stack length, so if suppose the stack length is more than some 20, suppose consider the stack length is 20, we cannot able to offer this 20 stack length as a single piece. So it should be segmented, right, as n number of pieces. So how much it is segmented, we can able to have some reduced value of cognitive, right? And this is a case study what we have analyzed in going on research work. And if you use an angle barrier of one layer, two layer, three layer, so now comparison, coming to the comparison, so here we can able to see 0.14 is the minimum torque ripple, and the average torque is 13.39, and the IPM angle is three layer machine, right? So as I mentioned, three layer machine is better suitable for some different types of high power based applications, right? Now, these are some of the torque characteristics of one layer, two layer, what we have seen here. And now we will see how to design this, because we have some basic knowledge, right? So with this, we will see how to design an internal permanent magnet motor by using finite element analysis, right? So to have a finite element analysis, so if you are an basic machine designer, right? So better I prefer motor saw. So if you are a basic designer, better you can go for motor saw, right? So this is the motor saw package. Um, I hope that I can able my screen is visible to you all.
Yes, sir, it's visible.
Visible. Okay, okay, okay. Thanks. So now, so if you open this, you can able to see a screen like this, right? So this is a home page. So here you need to select an BLDC motor or switch reference motor, induction or DC motor. So whatever you want, you can select from here. And since we involved in IPM based machine, so IPM based machine is derived from the origin of BLDC motor. So I am citing this BLDC motor here. So why I am saying this? Uh, Go with motor solving because it is a template based one, right? So uh, it is somewhat easy when compared to other packages, right? So now we need to set our voltage, right? So to set our voltage, we should know the basic uh, criteria what is available in the market. So the basic availability of the voltage, that is the batteries available in the market, is 12 volt, right? So in the order of 12 only, we need to assign the batteries, right? So I am going for 60 volt. So 12 plus 12, another 12, again another 12. So we will go for either 48 or 60. So five batteries I am going to arrange, and I am going to get a 60 volt, right? So keep the rated current as 10 and RPM. So this RPM is depend on the standard values. So I'm going to keep some 2000 RPM. And now, so this is the beauty of the finite element method based machine design. So here I am going to fix my outer diameter. I am not going to see anything. I am going to fix my outer diameter. So if I fix my outer diameter, I am going to just keep it as 100. Now you can able to have a tab here and just give OK. So now if you see, the remaining air gap thickness and stack length will be changed automatically, right? So that's the reason why I'm saying it is very suitable for beginner of machine design, right? So once you know this basic platform, then you can move on to uh, a generic based finite element based design. So now I just round it to 65, right? And air gap thickness I'm going to maintain as zero point 0.5, right? So why am I keeping as 0.5? Why can't I reduce more than 0.5, right? So if I reduce to zero point 0.2 or zero point 0.3 in case of a BLDC motor or an PMSM motor, what happens since the magnet is found in the outer periphery? If air gap is very small, right? If air gap is less, the air gap is very small here, it leads to magnetic locking, right? So that's the reason why we need to maintain the air gap in a minimum value. But here in case of IPM based motor, right? So now I will select the IPM. Suppose consider this is an IPM based motor, right? So not only this IPM, there is many types of IPM based motor also is there, and bed loaf motor also, spoke type. So many machines are there. So now as per our topic, we are focusing on this IPM based motor, right? Yeah. So now we are going to set our number of poles. Right? Suppose if I am keeping the number of pole as 6, see automatically you can be able to get this alignment. If you want to further align this, so the another option for you, I just go back with 4 itself. then we need to go for rotor design, right? So this is an important design parameter in this IPM based motor. So here you can able to see the bridge thickness, right? So whatever you are having, if you have parameter in the right side in the rotor, so it will be displayed in the workbench also, right? So in the work environment also you can able to see what is this bridge thickness, right? So as per this you can able to edit, right? So this is the bridge thickness, and now we will see the now consider this is the thickness. Now I want to reduce this, so I keep to 0.5, right? So what happens? This thickness of magnet is alone slightly increase, right? So here you can able to see the deviations, right? So here it is slightly increased. Suppose if you are increasing to the maximum value, I am going to give it as 5 means it will show error, right? See, it is reduced, right? So this is not a feasible one, right? So if you want to reduce, you can reduce, but as per the torque requirement, the magnet which is found in nearer to the outer periphery of the motor will contribute a huge amount to the air gap flux. So we are going to keep it as it is 0.5. Okay. Right. I will keep it as 1. So if you want, you further increase in this sequence, right? So here it is 0.6, some value, right? So the thickness gets reduced. If you want to increase again, you can able to increase to 2, right? So the thickness of magnet can be increased here, right? And then I don't want the structure. I want to change the different type of structure. Means just use this one. So the structure of the rotor gets changed. Again, I want to change the thickness of the magnet. So again, go to the rotor here, and you can be able to change whatever thickness you want here, right? So if you click here itself in the work environment, you can be able to see what are the parameters you need to change. And then coming back to the stator, right? So here the stator winding, try to keep always sine wave here, right? So if you cite sine wave, then only it is an IPM based motor. If you're keeping a stepped wave, then it is um, permanent magnet BLDC based motor. So don't keep in that, keep in the sine wave current, right? And if you are going for more number of ampere, then keep the parallel path as 2, and kindly select this coil arrangement as side by side, right? So keep the coil arrangement as side by side here, and ensure this coil fill factor some 50 percentage, right? So why I am keeping a minimum of 50 percentage means, so the space occupancy of this slots, so I am keeping as 50 percentage, and number of stands, right? So number of stands if you want you can increase. Moreover, so here if you want to increase the number of turns, you can be able to increase as 50 I am giving, right? Just a tentative one. And here the lap winding is there. If you want to go for an concentric, you go. But before going there, we need to change the side by side into over and under, and then only we need to go for this concentric based machine. So here you can able to see the winding diagram. So from where the current is coming and from where the current is entering, right? So this is identified by this red color for the R phase. So if you want to see where the current direction is going for all the phase at a time, so you can able to see now, right? So this is the winding pattern of the stator. And now you just change this winding pattern, right? And if you want to assign your own winding pattern, then we give it as a manual here, right? So don't uh, go for this manual based one at the initial stage, right? Right. So once you got expert in this, then you can move for the manual here. So for basic operation, go with automatic based application. That's it. So these are the minimum changes what you want to do, right? Okay. Wire insulation thickness, if you want, you can give, but generally it will be there. And then go to the result. So the basic and primary thing for design of a motor is torque, right? So first we need to design the torque of a motor. Whether we are getting or not, we need to check it out. So just give the view result here. And in the bottom, we can able to see the machine is solving itself, right? So now we had arrived some torque characteristics, but this torque characteristic seems to be a negative value. So what I'm going to do, I just um, give some advanced angle here. So advanced angle is nothing but it is related to the converter circuit, right? So I'm changing the firing pulses from one instant to suppose the firing pulse is turning on at 50 degrees. I'm going to turn on at 25 degrees. Right? So advanced. Previously, I'm going to turn on the pulse pattern. So then for that, how the machine is behaving, right? You can able to see the shape gets changed. Now further, I'm not get satisfied with this torque characteristics, right? So because it is a negative one, right? So here you are getting a negative torque only, right? Negative 0.509. So it is not a suitable one. Further, I need to go for some optimization technique. So what are the things I need to do for this betterment of the torque? So what I am going to do here, first we need to fix our topology. Right? First we need to fix our topology. So if this is the topology means then we will want. So whatever I am saying here is only a basic in this package. Right? So this is a basic package for understanding better about a finite element thing. Right? So apart from this, generic version also is there. Right. So just you can able to see I have arrived a positive torque. Right? Just I have arrived a positive torque here. Now I am going to change uh, the advance angle to 5. It is purely negative now. 30. No, right. So, right. So now I have arrived a positive torque. So likewise, some parameter are there to get a positive torque here. Right. So if you want to increase further, you need to concentrate on the this turns value, right? You need to concentrate on the turns value R. Go to this data, and here, if you want, you can able to increase the slot depth. So if you are increasing the slot depth, two advantages that you can able to increase the number of turns, as well as some ventilation also can be added in the inner periphery of the state. And if you want, you can reduce this slot opening. So slot opening nothing but it is a gap between two adjacent poles. So we give it one, right? So see here, if you change one parameter, so alternately you can able to fit the remaining parameter also. So now we'll go back to the tag. So now we are solving. So after solving, you will see the efficiency characteristics also. So now you see from 1.2, now we have reached the value as 1.6, right? So by changing any parameter, right? So finite element based design is not only by changing the stack length, stack height. So our stack height will be here. It is on 65. So if you want to increase, view to 80. Right? So these values has to be estimated by the analytical design for the accuracy. Again, the mathematical results will not suits in 100%. So again, optimization has to be done in finite element based techniques. So after solving a machine, right? So after solving a machine, generally machine designer what will do? He will go for the vibration analysis. He will go for the thermal analysis, right? So now what happens if he altered that one? The tar gets degraded, right? The tar gets degraded, right? So that optimization I should not prefer. I need to go for a better optimization technique, right? So previously it is 1.6, but now it is around a maximum of 1.4. Right? So the next thing is Cargin torque, right? So torque and Cargin torque are the most important parameter for a machine designer. Right? So this is an basic environment for a machine design, right? Suppose you can able to understand these things in the machine design. So here if you see the Cargin torque is 0.01 as the maximum value, not even 0.01. It is around 0.00926 is the maximum value for the torque. Torque, that is Cargin torque. Okay. So how this Cargin torque is arrived? So this Cargin torque is arrived due to the presence of magnet. So whenever the rotor is made to rotate without an excitation in the supply, the torque will be developed by the force in the permanent magnet, and that is a Cargin torque. And this Cargin torque will be in opposite to the nature of the torque developed by the stator. Right? So that is why we need to have a less value of Cargin torque, thereby the net torque will be a higher one. So here we have a less Cargin torque. So the next step of a design is transient case. Right? So for transient, uh, generally what we will do, uh, we need to go with an co-simulation. We need to go with co-simulation package. Right? So after solving your torque, right? After solving your torque, just in the bottom of the left hand side, you can able to see view result, and here you can able to see export this file to another advanced finite element analysis tool. Next to that, you can able to have MATLAB exportation option, right? So you just take this option to the MATLAB, right? So just click here, and it will ask which format. So just give it as tar-q, right? I just save it as in the text tab. So now you can able to see the tar-q. Right? So this is the MDL file, right? So tar MDL file. Right? So this file you can able to open in your MATLAB, and you can keep this motor in the existing EV system, and you can able to analyze for different drive cycles. Right? So without analyzing a motor after designing an EV drive system, it is not a full-fledged machine design. Right? So after exporting, so that is a separate topic. So still we didn't complete our machine design procedure here. Right? So the next option is here, motion analysis we need to do. So in this motion analysis, we can able to perform torque, voltage, co-energy, and but our basic necessity is torque, right? So if I give view result, it will consume some times, right? So it is around 41 steps has to go, right? So in the meantime, we will go back to the presentation, and we will see what are the remaining things has to be discussed, right? No. So next one is selection of material. So what type of material we need to select for an internal permanent magnet based design, right? So we need to have a non-oriented based material. So don't fix with one material first of all. So select two different n number of material, and in that just go with a BH characteristics. And if you go with BH characteristics itself, we can able to identify which material will give better result. So which is having a maximum value of knee point that will provide a high value of tag. Right? Not only that, we need to go with this losses characteristics also. So with this losses characteristics, so which characteristics is having uh, a lesser value of loss curve, which characteristics having a lesser value of loss curve, and that material only we need to suggest. Then only we can able to have a low value of iron loss, and we can able to get a higher value of torque, right? Next is thermal analysis. So this is a major drawback in the IPM based motor, right? So this thermal analysis we will discuss. Meanwhile, we will see the results is arrived, right? So result has been arrived. So now we can able to have the value as 5 Newton meter. Right? We can able to have a value as 5 Newton meter. Right? And then next is thermal analysis. Right? So we need to just see how the behavior of back EMF, current, torque, torque speed characteristics, efficiency, flux, air flux. So everything we need to analyze it one by one. Right? So I just give an outer loop how to go with this tool for a basic analysis of the machine. Right? And then coming to this thermal behavior. Right? So not only that, before going to thermal behavior, we should know the flux pattern. What is the flux pattern in this? Right? So now we go on to the flux pattern. because always we need to prefer a shortest flux path, right? Then only we can able to have an less ion loss, right? So here if you see these regions, right? So this region the flux density is very less, and here also the flux density is very less. So these regions are said to be as active region, right? So here the we can't able to say it is much active here, but the active region is found wherever the flux is traveling. So those regions are said to be as active region, and those region only will contribute to the iron losses, right? So here that's the reason why we are going for the shortest flux path. And here the maximum flux path is 2.68, and that is available only in this rotor. So here it is available, right? Now next one is force fields, right? So we are saying that is a unbalanced force are there. So due to this unbalanced force, only vibration will occur in a machine. So those forces we are going to see now. So how your force is found in a machine and how it is going to impact in the structural behavior, right? So the basic finite element analysis is vibration, thermal, other basic finite element analysis. These are arised by the effect of electromagnetic analysis, right? Right. So now this is the force, right? So you can able to see where the force is higher in your pole, right? Um, so here this red color indicates, so in this portion the force values are high. In this portion the force values are somewhat low. Now you can able to see some force is coming from here, right? So can I zoom it out? Right. So see here, some forces are reflecting back, right? Some forces are reflecting back here. So these forces will contribute to the vibration in a machines, right? So these are the effects of the force inside a stator, right? So everywhere. And if you see here, right? So if you see in the bottom case also, the more value of forces are available, right? So these forces which is moving towards the rotor won't affect the stator much. And again saying the forces which is coming from the stator towards the rotor don't affect much the stator poles. But if you see some forces won't enter into the rotor. So this will make a big impact in the vibration of a machine. So in these poles also, all poles are having the same effects, right? Since it is a singly salient, right? So this machine is singly salient. So much vibration impact will not take place in this IPM based motor. If it is in the case of uh, a doubly salient machine as SRM motor, switch reluctance motor, then vibration is a key drawback what has to be addressed. But now since it is an singly salient machine, this impact is not much on the machine, right? Right. Now, coming to this thermal fields, right? So now up to now we have studied the electromagnetic analysis and how the torque waveform is achieved and how to increase the torque waveform in a motor by doing some basic optimization technique. And We have seen the effect of forces which is developed in the stator, and followed by this we are going to discuss on the thermal behavior of a machine. Right? So the next one is the thermal. So this thermal is determined by the thickness of the laminating core material. Right? So the thermal analysis is always maximum amount is determined by the thickness of the laminating core material, and moreover how much load it is uh, withstand, because automatically uh, the current consumed by the motor also will be increased, right? So it leads to more I square R losses. So now, so this is a 20, just a few percentage of the motor here, and you can able to see a maximum, right? So this is a tentative machine, and this is the distribution how the heat is flown in the motor, right? So if you want to see the characteristics point of view, so if you want to highlight this, so if you want to highlight the, this is the thermal results. Nice. Now, further I need to reduce this temperature. Suppose whatever value is showing, the minimum value is 117 and the maximum is 225 here. That means the minimum temperature is 117, the difference is around 50 degrees Celsius. Right? 50 degrees Celsius. Further I need to reduce this. So here is the cooling system what we have. Right? So in this cooling system we need to include these values. Right? So we need to improve this data, right? If you have your data, you can able to import by using this Excel sheet. Right? Suppose no data is there, just give this data such that how it is starting and how it is after some time, what is the behavior of the rotor can be determined by this value itself. Then, so now you can able to see here. I will expand and show it to you. So end speed is 100%. So what I'm going to do, I'm going to have another 10 duration of time, and the rate of torque percentage is 70. I am going to consider, and start speed at starting itself, I'm going to have only a 80% of speed, and end speed is around 100%, and in previous case we have the end speed of 100. Right. Right. So I have set some values here, right? So now we are going to, so for betterment, we will reduce the time, right? So just give some 5, right? Because it will take much time. So still some topics are there to discuss. So cooling duct, so okay. So these are the some of the drawbacks with this basic type. So what we are going to do, first we see the losses one by one. So these are the losses occurring in the machine, and back EMF, right? So this is another important parameter in the machine design, right? So one is torque, another one is coil torque. So here we can, it is easy to have an efficiency map, right? So if you want to have to publish a publication, then it is very suitable to have this. Right? Now, uh, now what I want to do, I want to have a different strata topology. I don't want to use this strata topology. I want to use a different strata topology. So what I want to do? So what type of strata topology? Whether it is only suitable for existing topology or different topology also shall I use here? So these are the different structures of strata, right? So here you can able to see they are around in this backend, right? So in this backend, the slot shape also has changed. So another question arises, only these are the feasible options are there, or we will go for some different things. So if you want to use a flux barrier in the rotor, whether it is possible, yeah, that also is possible. For that, what we want to do, we need to use a DXF file. We need to go for an AutoCAD file. So by using this AutoCAD file, you can different type of strata topology in this system, right? So that is another thing. Now, now what happens? I don't want to use this uh, structure, right? I don't want to use this structure. So in this case, uh, again I will change it to the base one. Right. So I have changed it to a base one. Now this motor result has been derived, right? So already we have analyzed the motor design. So now what I am going to do, I want to have a different structure in the rotor. Suppose consider here I need to have some flux barrier. So I just exporting in another environment, and I'm going to save it as magnet itself, IPM, right? So I just save the desktop. Right. So this is another environment what we are going to see here. And the first thing in any environment we need to assign our units, right? So assign the unit as uh, millimeters, right? So this is a basic step. We need to assign our unit as millimeter. Then we can able to open our exported file from the motor solve. So here we have our magnet IPM. So we have opened our magnet IPM based machine in another package, right? Now, if you want to have a different topology, right? If you want to have a different topology, now we can able to edit it, right? So suppose this is the state or what we have. Right? What I'm going to do is just delete this data. Just one, right? So, right. And another thing, if you want to delete it and we need to draw, now I don't want to export the entire thing. I want to export only um, the AutoCAD file, right? So in that case, go to the design, and here you'll be having the exportation as an AutoCAD file, right? So here I just go into the export, and I'm going to this magnet. Now after setting this units to the millimeter, I want to import it. So this is desktop. Okay. So here we have our DXF file and give it to root. So now we have derived a DXF file from there. And now what I am thinking, I just want to have a circle here, right? And this is a circular based flux barrier. Now this circular, so I'm just using all this region for circular as flux barrier. Now see here I am assigning the metric. So we will have the circle everywhere. So this is a new type of stator with circular based flux barrier. So like this, we can able to model the material here. I'm going to choose M19, and here stack length is nothing but suppose I give 0 here. You can able to see the thickness as 1. Again, if I go and give this 0 as some 50, you can able to see the thickness in 3-dimensional point of view, right? So that is a use of this magnet, right? So magnet, so in this platform, we can able to optimize the structure of a machine as much as we want, right? But before going to this, kindly prefer a template based one and make much familiar with this. And my request in this concern is, so after simulating, try to export to an MATLAB or AMEC sim, right? So for a course simulation purposes, then only we can able to understand how the designed machine is behaving for an electric vehicle purposes, right? So at starting we have designed a machine for EV application and we have analyzed the machine how it is behaving. But at last we need to transform this design a machine into a MATLAB based environment or AME sim based environment, right? Then only we can able to understand how this motor is behaving with respect to the EV applications, right? So not only this one, another one also is the flux based machine, right? So here we are having a fluxer based flux motor. This is also a template based one, right? So so this one also is very suitable for template based design for beginners, right? So those person who are beginner can prefer either this motor saw or flux based motor. So here go with different topology means just change the. So here you can able to change what is outer diameter you have, what is the length and what is how many number of slots. Suppose air gap is not fixed, so just use this option. You can able to edit the air gap, right? And if you want to edit all those things, just type it. You can edit it and then give tick option, right? And then go with magnets, that is rotor. So what type of rotor you want, right? So what type of rotor you want, you can able to select in this row, right? So this is also a one type of internal permanent magnet, right? See, and if you see the entire topology, so this is a new IPM based motor. So because the magnet is placed inside the core, this is not outside, so it is inside the core, and it's also a new type of IPM based motor, right? So IPM based motor is only concept is the magnet has to be placed inside the core. Any direction of magnetization can be used or any arrangement of magnet can be used, but stick on to the torque value. Right? We should stick on to the torque value here. Stator, if you want to change the stator also, you can change which type of stator you want. Right? So everything is feasible. Right? For testing, so sine wave we are preferring because what type of line current we should give. So I am going to give some 12 and just test it. Right? We will obtain some results. Right? So whatever result we are obtaining is not an accurate one. It is just a tentative based design. Right? So here you can able to see the machine is running out, and there are a few options also for thermal testing. Right? So we have seen the thermal behavior, diaphragmatic behavior here. If you want to see the thermal, then you can change the boundary conditions, and again you need to perform these thermal characteristics. Right? So, what is the value of speed, joules, loss, everything you need to calculate, and these values can be obtained in the sine wave itself. So here we can do the torque speed, and here you can able to see the flux linkage, electromagnetic characteristics, and all the results can be obtained here itself. If you want to see the characteristics, just click here. You can able to see, right? So this is an isometric view of this type of IPM based machine, right? And moreover, the recent technique moving on here is NVH, that is noise, vibration, and hardness level. So just click on to this, and you can able to get the value on decibels, right? So noise, decibels, and vibration modes, which mode it is going to create some noise. So each and everything can be addressed here. Right? So this is better for a beginner. Right? This one is better for a beginner with a machine design. So after designing, you need to prefer core simulation. Then only we can be able to obtain machine characteristics with EV application. Otherwise, we have only the characteristics of motor. So I have shown you how to convert the designed file into a MATLAB file also. Right? So meanwhile, we will come back to the presentation, and this is my final slides. So here the thermal behavior is available, right? And this is the characteristics of the thermal behavior. So here the temperature seems to be high with stator coil side and followed by stator tooth and again stator back ion, and then only is going to the rotor. Right? So the major drawback in this IPM based machine is thermal behavior only. So you can do more when you research in this thermal analysis because we can't able to load the machine to the rated current value. If you are loading the machine to rated current value and running for some maximum duration of time, the magnet behavior gets changes, right? So that may degrade the power density of a machine, and thereby the performance of the machine also gets degraded, right? So we'll see whether the results are obtained or not. Yes. So the results are obtained here, and this is our dB characteristics, and this is the pressure characteristics what we have seen, and this is the water position degree with mechanical and radiation, that is acoustic radiation also can be obtained, and modal analysis, so in which frequency the amplitude of vibration will be more, so that can be predicted in this modal analysis. And if you want to export save results, you can save it And if you want to save it as an PDF, okay, you can save it as a PDF, right? So here we have saved the results in the data sheets also, right? And since timing out, I am winding the session. Um, Thank you. If there is any queries, I like to answer it.
Participants, if you are having any doubt, you can ask.
All your mics are unmuted. Just you can speak now. So there is one question from Sarojini Harikrishnan.
Uh,
So which optimization technique is recently using for torque ripple reduction in EV motor?
Sir, ready to control technique only you are preferring. Because in industry side and that only we are using now. Just now they stepped on to predictive control technique, thereby we can able to control the current of a motor and that will impact in the torque of a machine. And my suggestion is to go with structural optimization and in design itself, nearly 60% of torque ripple we can able to minimize.
Is there any questions from audience side? Okay, so I have one question with you, sir.
Sir.
Sir, you are designed initially you have designed with motor solver.
Yes, sir.
Then you have changed to magnet. Is there
Yes, sir.
any communication between these two softwares, sir?
Yeah. Just we can just import it to other. That option is there. I have shown you. Yeah. So here you can able to see the option in the screen, the bottom side, the left hand side bottom. You can able to see the screen, and here the magnet option is available. And save it, and after going to the motor sorry magnet, you can able to import it. Right. So go to file and import it. So already one file is there, right? So we can able to import it. There is no other hidden secrets here.
So by designing any software, you can able to communicate with the magnet.
Sir, we can able to communicate with MATLAB because
Magnet
this
is
is a
also
flat.
able to communicate with MATLAB.
Yeah, this also can be communicated with MATLAB.
Okay, sir. Fine. Is there any other questions from audience side?
Good evening, sir.
Madam.
Sir,
Good evening,
actually,
madam.
you have said that we have to design the motor from the power of the equations. So
Yes.
once we have decided the power as well as star, any
Right.
standards are available for checking the motor parameters, sir?
Motor parameters. Yes, madam. It is there. Industrial standards are there for the machine design, which is approved by the government of India.
Yes, sir. Could you please suggest which
The
standards?
frame is there. Frame setting is there. So AES standards. Indian standards are there.
AIS.
Yes, madam.
Okay.
Indian standards are there.
Okay, sir.
Okay. Because depending on the frame size only, we need to fix the outer diameter also. Lot of mechanical consideration also is there for fixing the outer diameter. Not only the mathematical equation, but also the frame size of a motor also we need to consider.
Okay, sir.
Okay.
Thank you, sir. Thank you.
Thank you. Thank you.
Vinod sir, shall we conclude, sir?
Yes, sir. Thank you, sir. Thank you for accepting our invitation and presenting. Participant Sir has a very vast experience in magnet software, ANSYS, PROE. So by giving 1 hour or 1.5 hours will not be sufficient, but Sir has taken excellently. Thank you, sir. Arul Prakash, sir, you can proceed.
Sir, thank you so much for your wonderful presentation, sir. Right from
Thank
the
you, sir.
beginning.
Thank you very much for giving this opportunity. I once again thank Dr. Vinod, sir, head of the department, and our Arul, sir, for giving me this opportunity, sir.
Thank you, sir. Thank you for the wonderful presentation, sir. Participants, you can fill up the feedback form and you can give. So the yesterday session YouTube link also given the chat box. Please make use of it.
Thank you, sir. Prabhu, sir, thank you, and we can leave.
Thank you, sir. Thank you very much, sir.
Arul, sir, I am leaving.